This is combustion of the fuel-air mixture in a special gasoline engine. It was photographed with a special camera operating at 40,000 pictures per second, which means that the action is here slowed down 2,500 times. You can perhaps better appreciate the meaning of 40,000 pictures per second by seeing what it does to a photographer's flash bulb. The bulb actually fires in 1/100th of a second. And this firecracker, it actually explodes in 1,000th of a second. In order to photograph the combustion inside an engine, a special glass window was placed in the head of a cylinder. The camera will look through this window and see the burning of the fuel-air mixture. With normal combustion, after the spark plug ignites the charge, the flame front spreads outward and across the combustion chamber. Now, in actual photography, at 40,000 pictures per second, this is how normal combustion appears. Throughout combustion, you can see a steady and controlled transformation of chemical energy into heat energy. The black spot at the upper right is caused by uneven lighting. It has no significance relative to the mixture of fuel and air. Notice the continual motion in the burning zone. Combustion can also be shown in the form of a graph. Pressure is indicated vertically, time horizontally. That is, the time required for those parts of the compression and power strokes shown here. The pressure increases as the piston rises on the compression stroke. When the spark ignites the mixture, the pressure increases very rapidly. As the piston is pushed down on the power stroke, the pressure decreases. This record of normal combustion shows smooth, even development of full power. Now let's look at knocking combustion, the result of using fuel of insufficient anti-knock value. The flame front will start as in normal combustion, but near the end zone, it will appear to hesitate, and then the unburned portion of the mixture will detonate or explode. This is knock, as seen in animated drawings. Now let's see it at 40,000 pictures per second. Watch for the slight hesitation of the flame front just before knock, and note how the knock sets up violent vibrations. The speed of the knock is so fast that it is extremely difficult to measure. Knock is caused by pressures and temperatures that get too high for the anti-knock value of the fuel being used. The unburned gases explode with terrific force. On the graph, knocking combustion can be illustrated very clearly. Again, on the compression stroke, pressure increases. When the spark ignites the mixture, the pressure increases very rapidly. As the pressure reaches its peak, knock shows up as violent and rapid pressure changes. Compare this graph with the graph of normal combustion. Knock results in loss of power. It also causes overheating and excessive wear on the engine. Knocking with pre-ignition is another example of poor combustion. Pre-ignition is usually caused by a carbonaceous deposit that becomes incandescent in the engine cylinder. It's commonly called a hotspot. Pre-ignition by a hotspot produces the same kind of flame front as that caused by a badly over-advanced spark, causing combustion to get completely out of control. Knocking will occur if fuel of insufficient anti-knock value is used. Seen in slow-motion photography, pre-ignition occurs before the spark plug fires. Knocking occurs after the spark plug fires. The pre-ignition effect of the hotspot is the same as that caused by an additional spark plug with its timing advanced too far. A good part of the heat energy prematurely released by pre-ignition may be wasted. Now let's look at the graph for this kind of combustion. Pre-ignition by the hotspot causes the pressure to rise rapidly and very early. Ignition by the spark increases the pressure further. Knocking again occurs when the temperatures and pressures get too high for the anti-knock value of the fuel being used. Compare this graph with the graph of normal combustion. Pre-ignition has the effect of advancing the timing to such a great extent that the peak pressure occurs before the piston has reached the top of the compression stroke. The loss of power is now very considerable. And again, there is overheating and excessive wear on the engine. Obviously, knock and pre-ignition should be prevented. Only normal combustion will produce a steady and controlled transformation of chemical energy into heat energy. Only regulated, even burning will provide full, smooth power. This kind of controlled combustion, assuring full power and protection against damage to the engine, is achieved with a fuel which is high enough in octane rating and which also contains an anti-pre-ignition additive. Ethyl anti-knock compound is used by most refiners to increase the octane rating of their gasolines. Ethyl Corporation also manufactures an ignition control compound which reduces pre-ignition. This then gives the refiner, the dealer, and the car owner a gasoline that meets today's severe operating conditions with assurance of top performance and economy.